much, Kiel, for your kind introduction, which was, as always, really great and very entertaining. And now I will try to a bit entertain you sometimes. Also, this is actually joint work with some of my PhD students. And we are at the University of Muenster in Germany. And a couple of words about our university. It's one of the largest in Germany, actually. We have more than 45,000 students, many of them international students. And my group works on parallel and distributed systems. And here you see some topics of our research. It includes distributed systems and clouds, networking, in particular software-defined networking. These are two topics which I will talk today about. But we are also quite active in high-level parallel programming, in high-performance computing. And especially nowadays, we are interested mostly in high-level approaches to programming multi and many cores like GPUs, for example. And we have been also involved in many national and international projects. And you see here some of them. And if you feel that you are working in similar fields, then please talk to me. Maybe we will do something together in future. Good, so our topic today are these real-time online interactive applications. We call them ROIA. And one example which Kiel was already talking about are online games, namely massively multiplayer online games, where you have gamers who are, first of all, huge in number. So there are games where tens of thousands of people can be involved simultaneously. And all these gamers, let's imagine, they want to play together in one time, but from very different geographic locations, maybe from different continents. So some of them are in San Francisco, some of them are in Europe, some of them are in Australia, and they want to play together such that it is realistic. So they see each other, they see each other's avatars actually, and they want that the state of the game, so what is happening in the game, which characters are moving, which characters are shooting, which characters disappear and then survive again, something like that. All that must be very realistic for participants. And that's why one of the main challenges here is that the update rate of the application must be very high, up to 50 updates per second. And just imagine, people are on different continents, but they must see each other in real time or near real time, as if it is real time. And also, we spoke already, as the audience spoke about latency, and it's exactly the response time of the application. So if I am shooting at my opponent in a combat game, then I want, of course, to see the result of the shooting immediately. And in the area of computer games, it's usually assumed that if the gamer is waiting more than 1 second, then it's already too slow. It's already not realistic, and such game will be not a success. And last but not least, here is the variable user load, because it's quite difficult to predict how many people will be interested, how many people will join, at which moment in the time, and so on. So how these applications are developed usually, So usually it's quite a complicated piece of software, traditionally written in C++ because it's okay, it's low-level language, but it's high-performance language, which is very important here. And the main issues which must be addressed by the software developer for such applications are here in these two rectangles, this application process, and you see here 4 issues. Application logic, it means the contents of the game, so to speak. So what are the characters, what are the rules, how the characters are moving, how the characters, are they allowed to shoot or not to shoot, and so on. This is usually the responsibility of artists, so to speak, of people who invent a new game. And then it comes to 3 issues for software developers. We must manage distribution of this game, because if people are on different continents, then of course we have many computers involved. We have, first of all, client computers of every participant, and we have server computers, which are again not one, but many, which are again located geographically quite far from each other. We must organize network communication, and we must organize monitoring and controlling, and all of that must be somehow put together in one piece of software. And the state of the art is unfortunately that each new game is developed mostly from scratch. So people just get application logic from the artist, and then they start to write code. And actually this situation is of course very bad, and it's one of the reasons why many companies who develop games, they went bankrupt. So they just disappeared because they had to invest a lot of money and manpower into developing a new game from scratch. And then this game was not a success. And so the company is in debt and company disappears. So what we try to do here from our research point of view, for us, it's a very challenging and interesting task actually. And we try in this white rectangle with 4 issues, we try to do what you see here. We try to reorganize this process in such a way that the application logic, it remains the responsibility of the human being, because we still cannot rely on AI in inventing new games. So I hope at least that we will be still able to do such really artistic work. But the other issues, the issues of programming, of software development, they are covered now by the framework which we developed. And this framework is called Realtime Framework. And the framework is now responsible for producing code which works then according to the rules of the game. So here we have responsibility division between the human being and the programming framework. Good, so now we can see an example. I hope we can start the video. Actually, oh, no.
Just trying to make it work from this side. Give us a few seconds. There we are.
Oh, now we are. Good. So it's a very simple game, actually. It's done by our students. So the graphics is very elementary here, and it's not the issue here. The issue here is to have many avatars. You see here, these robots are shooting at each other. They can also burn and so on. And here we have different colors of these robots. It means that already different servers are responsible for them. And we also must, of course, see the situation here. You see there are many of them, and they are stepping on the place, and then they're jumping. So the movements are not smooth anymore. And what we expect from the framework here is that the framework recognizes this situation and automatically add a new resource, a new server, for example, such that the robots are covered but by more servers, by more computational power. And then, of course, if you add a server, you must organize also networking with this server and so on. So this is covered by the framework. And of course, we need a kind of abstract model for such kind of applications. And this is quite simple model. You see here on the left, you see here the guys who are participating in the game. You see then the servers. Each server covers a group of the clients. And then on the right, you have the so-called map of the game. So it's a picture which we see on the screen with avatars, with objects, with landscape, and so on. And then we have a very simple computational model here. It consists just of the loop, which is called real-time loop, and which has only 3 steps. And these steps are very intuitive, actually. So the framework receives user actions, then it calculates the new game state, and then it sends this new game state to the participants. And then again. So, and this must work in real time or almost real time. And the distribution across servers can be done differently. And this is also quite an important issue in developing such distributed applications, how to distribute the map of the game between servers. And you can do it very simply, which is called zoning, for example. It's you just cut the map in some sub areas, or you can do instancing, or you can do replication. And the framework here, the responsibility of our framework here is to combine, to allow the software developer to combine freely these different kinds of distributions. So you see here, for example, we have 4 zones or 4 colors. So yellow, red, blue, and green. And then the green zone is replicated, and the red zone is instanced. So you have very different possibilities here. And of course, we test this framework on under different conditions. And we not only develop, or we can not only develop new applications using this framework, we can also improve the existing applications. And for example, Quake 3, it is and still, it was and is still quite a popular game, which is very highly optimized, so to speak, and really good game. And the good thing for us as researchers was that it was a very rare situation that the code was really available, because all this area of gaming is very secretive, so to speak. It's all of issues of software, algorithms, and so on. It's top secret of companies. And in this case, we had an exception. We had this code available. That's why what we did here, we improved this Quake 3 game from one server game to many server game. And in this way, we we achieved much better scalability. So we can accommodate just many more users who can use this game and play it smoothly. Next issue here was to use clouds, because clouds are very popular, and you know the main idea. The main idea is like you use electricity in your home, for example. So you are not interested where it comes from, how is it is produced, how to maintain the generators of electricity and so on. You just have your contract with your local provider, and if you use electricity, you pay for it. If you don't use, you don't pay for it. And cloud is the same in computer industry. It means that a company doesn't have to have its own computer center. It can just buy or sign a contract with Amazon, for example, and say, I want so many processors, so much memory, and if I use it, I pay. If I don't use it, I don't pay. And I am not involved in the maintenance of computers, in updating software on them, and so on. So we have here many benefits, of course, but on the other hand, we have also problems, because we need here resource management systems which allow us to really manage resources in such a way that we get from the cloud exactly so many resources as we need, not more than that. And if we don't need some of these resources, we should give them back. And then we have this pay by use, so to speak, yeah? And here we use, or we develop here, load balancing mechanism, which consists of 4 actions. And the question is how to decide among these actions, how to choose the right action in a particular situation in the application. And these actions are user migration. So, for example, the user will be migrated from one server to another server, but of course it must be done in such a way that the user doesn't notice it. Yeah? So it must be done absolutely transparently for the gamer, because he doesn't want to be involved in these technical issues. Replication enactment, if we add a new server. Resource substitution, if we substitute a weaker machine by a stronger machine. And resource removal, if we don't need some resource and we can just remove it. And here we have this very simple decision diagram where in these particular points, we just check particular conditions, and then we go left or right, and then eventually we come to the right load balancing action. So here is the idea how it works. And of course, we did quite a lot of experiments. I will not go here into detail. So we just check how it works in particular practical situations and how this load balancing improves the performance for very variable number of users, which is dynamically changing. Then the question of scalability. You remember our simple game with robots, where we had so many robots that the available servers were not enough. So here we need to be to be quite precise, because we need to use these load balancing actions depending on the different application workloads, and we don't have to forget that that the load balancing itself, it's a kind of overhead, because it also takes time from the application. And so we improve this model and this diagram, and again, a case study how it works. Good. I will very briefly tell you about one project which was called Monica, where Europe cooperated with China. So it was the idea that we work here with mobile devices. So gamers are connecting not from computers, but from mobile devices. And this was taken into account, naturally, of course, and we had to develop a special solution for that. And final project I will briefly tell you about is this Offerty project. It's purely European project. And in this project, we are addressing networking. And the problem with networking especially in this area of very demanding applications is that traditional networking works on a best effort basis. What it means the network will try its best, of course, for you, but if some particular link is congested, then usually traditional network cannot do anything about it. And what is done here, what is recently a new, so to speak, direction in this respect is the so-called software-defined networking, where we have the SDN controller, which can observe the links, and if necessary, it can reroute the messages, the flows in the network. And in this project, we developed a special API for improving the quality of service in such a network. And again, no technical details here. What is important here? Important is that we want that the application developers work with application level metrics, that they don't need to go very deep inside into the network level metrics. And for that, we develop a special automatic translation between application level requirements and network level requirements. And it's done here, simple mathematical model, several cases, how it works, then the same demonstration, but using now this SDN approach. And the final point here in this talk is how we manage the quality of service using this approach of software-defined networking. We distinguish here two kinds of clients, and it's a typical business situation. So there are people who just get a free subscription to the game, for example, and they don't pay money, but they get no guarantee of quality. And there are premium clients who do pay money and who get guarantees. And then we see here this, these three curves. The red curve means the CPU load of the servers. And you see that it's rising. And the blue curve shows the response time of the normal or free clients, so to speak, yeah, who have no guarantee and who didn't pay any money. And you see here that already in the middle of the of this graphic, you see here that this response time is rising dramatically, and it means for these guys the game becomes unplayable, so to speak. And the green curve shows you what happens with people who did pay money, and of course they get the reward. They can play this game in much bigger numbers of players. Okay, and this is the last slide between us and coffee. Thank you very much for your attention, and thank you very much for inviting me.
Sergei Gorlatch.